Welcome to the podcast of machine learning. Today, we're going to dive into one of the really big challenges in AI right now. How do we build these foundation models so they're not just clever, but actually robust,
Right.
reliable?
It boils down to whether the model is just memorizing what it saw in training, or if it's actually learning principles it can transfer, principles that hold up when things change.
Exactly. It's like the difference between, say, a student who just crammed for a test versus one who genuinely gets the concepts.
Because if the AI is just parroting training data, it breaks the second you tweak a rule or show it something unfamiliar. So our mission today is to really unpack this study that compared the two big post-training methods, supervised fine-tuning, SFT, and reinforcement learning, RL, to see which one actually leads to that deeper general understanding.
And this is super important for anyone actually using these models because the results show a massive difference. It's not subtle. When faced with new rules or visual scenes, one method clearly comes out on top for generalization.
Definitely. And to test this properly, they couldn't just use standard benchmarks. You need specific tests. They set up what are called out-of-distribution tests, OD, where they deliberately change the rules or the environment.
Okay, so forcing the model off its familiar turf, how do they do that? What were the testing grounds?
So two main environments. First, something called general points. It's basically an arithmetic card game, all text-based.
A card game, okay.
And for this, the generalization test was all about the text rules. During training, the in-distribution phase, the model learned that face cards, jack, queen, king are all worth 10 points. Pretty standard rule.
Got it.
Yeah.
J, Q, K equals 10.
But then, for the O test, they switched it up. Suddenly, the rule changed in the text. Jack became 11, queen 12, king 13.
So the model had to ignore the old rule it learned and apply this totally new logic just based on the new instructions.
Precisely. And the second environment was VIRL. That stands for Vision Language Navigation.
Okay, that sounds more complex navigation.
Yeah, much more real world. It involves spatial reasoning. The model gets language instructions and has to navigate a simulated space, like a Street View environment.
Right. And how did they change the rules there?
It was about the action space, how the model interprets movement commands. In training, the ID phase, it learned absolute directions. Commands like go north, turn east.
Standard map directions.
Exactly. But for the O test, they switched to relative orientation. So the commands became things like turn left at the corner or go slightly right.
Oh, that's a big shift conceptually. From a fixed compass to your own perspective.
Huge shift. It forces the model to understand space differently.
That's like training someone using only GPS coordinates and then suddenly asking them to navigate using landmarks and left-right turns.
Exactly like that. And this is where the difference between SFT and RL just became crystal clear. When faced with these unseen rules, the card values, the navigation directions RL really shone. It generalized.
How well did it generalize? Were there numbers?
Yeah, so on the VIRL task, the pure language version testing, just the rule understanding, RL actually improved its success rate, OD, by plus 11.0%.
It got better with the new rules.
It would adapt it successfully, yeah. But SFT, well, SFT was the opposite story.
What happened there?
It seems SFT just memorized the original go north type rules. When the relative turn left rules came in, its performance just collapsed. A massive drop. We're talking notable 79.5% in success rate on that same VIRL language task.
Wait, minus 80% almost?
Yeah.
So if you were using that SFT model, it basically goes from working okay to completely failing the moment the instructions change slightly.
That's the implication. It's incredibly brittle. It confirms that SFT tends to just memorize the training distribution. RL, though, because it's optimizing for an outcome through rewards, seems forced to learn more general transferable rules.
Okay, that makes sense for text-based rules, but this VIRL thing also has a vision component, right?
Got it.
Visual language navigation.
It does.
So if RL generalizes text rules better, does it also generalize better when the visuals change? In these vision language models or VLMs?
Great question. Because VLMs need to handle both. So they tested Visual O too.
How did they set that up? Different visuals?
Two ways. First, back to the card game, General Points VL, the visual version. They trained it only on black suits, spades, and clubs.
Okay.
Then, the O test was only red suits, hearts, and diamonds. Our share. Same game, different looking cards.
Got it. Swap the colors. And for the navigation task, VIRL VL.
That was a bigger visual shift. Training was done only using routes in New York City.
Ah, okay. Lots of specific buildings, street signs.
Exactly. Then the O-test used routes from totally different cities worldwide, places like Milan, London, Buenos Aires.
Wow, so completely different architecture, landmarks, everything. The model had to generalize its visual understanding globally.
It really did. So you switched card colors in one and entire cities in the other. How did SFT cope?
Given the previous result, I'm guessing not well.
You guessed right. SFT performance dropped again when the visuals changed. It struggled with the red cards, it struggled to recognize landmarks in London or Milan, it failed to generalize visually, just like it failed in the text rules.
But RL.
RL, again, showed much better generalization, especially on that tough VIRL-VL navigation task in unseen cities. RL's success rate improved by a massive plus 61.1% LOD.
Plus 61%, that's huge. It suggests RL isn't just learning rules better, it's actually learning to see better in new places.
That's exactly what the deeper analysis suggested. Training with RL, using that outcome-based reward, it actually improved the model's core visual recognition abilities.
Well, think about it. How does getting a reward for reaching a destination make the model better at recognizing, say, a specific building type?
Well, think about it. To succeed in navigating a new city based on instructions like turn left at the cathedral,
Right.
the model has to correctly identify the cathedral even if it looks different from the churches it saw in training in NYC.
Right. If it misidentifies the landmark, it takes the wrong turn.
Fails the task, gets a low reward. The RL process then adjusts the model's parameters. So the need to achieve the goal successfully creates this sort of indirect pressure to improve visual perception.
Ah, I see. The reward signal implicitly trains perception because accurate perception is necessary for successful action and thus reward.
Precisely. It forces the model to connect seeing this new thing with taking the right action to get the reward. It improves reasoning and perception together.
That's a really powerful finding. RL drives generalization in both reasoning and seeing, but there's a catch, right?
There is.
The study used a llama VLM, and they initialized RL after doing SFT first. If SFT is so bad at generalization, why do it at all? Why not just start with RL?
That's the critical nuance. SFT, despite its flaws in generalization, plays a vital role. It acts as the format teacher.
Format teacher, meaning?
It stabilizes the model's output. It teaches it how to follow instructions and respond in a structured way. The study found this was absolutely essential before RL could work.
So what happens if you skip SFT and just try RL on the base model?
Complete failure. The base model might be good at predicting the next word, but it's terrible at following specific instructions for a task. It generates responses the study described as long, tangential, and unstructured, basically unusable for the RL process.
Right, so the RL system, which needs to verify if the model succeeded or failed, can't even figure out what the model tried to do because the output is nonsense.
Exactly. SFT provides the basic scaffolding. It teaches the model the rules of the game for interacting and responding coherently. Only then can the more complex RL process, with its verification and self-correction, actually function.
Okay, so SFT is necessary scaffolding. Let's talk about that RL verification process. The study mentions scaling up compute during RL training.
Yeah, specifically the inference time compute, basically allowing the model more steps to verify its answer or revise its plan during the RL training phase.
Did giving it more thinking time help?
Dramatically. Especially for generalization, they found that OD performance growth was almost 6 times higher when they allowed the model 10 verification steps compared to just 1.
6 times better generalization just by letting it check its work more during training.
It strongly suggests that generalization isn't just about the data or the reward function alone. It's also deeply tied to the model's ability to sort of deliberate, verify, and self-correct during learning, especially when facing new or complex situations.
That ability to iterate seems key to embedding the principles, not just the examples.
It looks that way. It's a crucial insight for designing more robust systems.
Okay, so let's synthesize this. For you, the learner, building or using these models, what's the big picture? We've got RL as the engine driving true generalization learning rules, improving vision, handling novelty.
Right, by focusing on successful outcomes. And then you have SFT as the essential initial tutor. It teaches the model how to communicate properly, how to follow instructions, setting the stage for RL.
But SFT has this dangerous side effect of promoting memorization, especially, it seems, hurting visual understanding.
Exactly. The issue isn't that SFT exists, but how it works seems to make it brittle.
Which brings us back to that weird visual problem with SFT. Why does training it to talk properly seem to make it worse at seeing?
This might be the most subtle but important point. The researchers hypothesized that SFT overfits to what they called reasoning tokens and ends up neglecting the less frequent recognition tokens.
Okay, let's unpack reasoning versus recognition tokens. What's the difference in the model's output?
So reasoning tokens are the words related to structure, logic, formatting. Things like because, therefore, step one. The answer is high-frequency stuff. SFT rewards getting this structure right, making the output look coherent.
And recognition tokens are.
Those are tied directly to the input, especially visual input, like the specific card suit hair or the name of a landmark, Eiffel Tower, or a color red. These appear less often in the output text.
Ah, so SFT in trying to make the language smooth and logical.
Might inadvertently teach the model to pay less attention to the specific details of what it's seeing because those details don't appear in the output structure as often.
It learns to sound smart but becomes less observant of new visual details. That's counterintuitive but makes sense.
It suggests SFT can actually degrade the model's core visual perception while improving its conversational ability, a problematic trade-off.
Which leads us to the final thought, the challenge for you, the listener, working in this space.
Exactly. Can we redesign that initial SFT phase? Can we make it teach the necessary format and instruction following, but without damaging the model's ability to see and generalize visually? Can we train the format teacher without essentially blinding the model?
Finding that balance, that way to get the best of both SFT and RL without the downsides. That seems like the next big step for truly robust AI.